Okay, guys, this is not the solution video to this question. The solution videos follow, but I wanted to kind of discuss one quick thing with you about this question before we start, and that's just to do a real quick brush up on related rates, which was section 2.6, I believe. And related rates worked like this. So check 2.6 for your notes if from earlier in the year if you need more of a brush up on this, or let me know and I can lead you in the right direction. But this is where we had, you know, a basic geometry expression or other expression. We said, how does this change with respect to time, right? So we're a lot more used to talking about rates of change now than we were early in the year. And so if I wanted to take the derivative of A, I said, well, how does the area change with relationship to time? And then when I take the derivative over here, pi is not a variable, it's a constant, so this would be 2 pi r, but the radius would also, we'd have to see what dr dt is, how that changes with relationship to time. In much the same way, you're going to have on this problem, volume equals pi r squared h. Well, how does the volume change with respect to time? Well, pi stays the same, but notice we've got two different variables here. Okay, we've got an r and an h. So that's the product rule. So in one case, we would have to leave the radius alone and take the derivative of h, which would be dh dt, plus take the derivative of r squared, which would be 2r dr dt, and leave h alone. Now that would be a traditional way of solving this, and you would have to find somewhere in your setup all of these different variables. When you watch Mr. Smith's solution video, I want you to notice, however, that there is no dr dt for this, which sometimes confuses guys, but here's the thing. If you look at the picture, and I want you to imagine water draining from that tank or collecting, whether the water is raising or lowering, I want you to think about, is the radius changing at all? In other words, as I go from the center to the edge here, is the radius going to change? And in this particular example, the radius doesn't change at all. The radius would stay the same. So you'll notice Mr. Smith make a substitution. Now, if this was the same question, but it was shaped like a funnel, okay, if it was shaped like a cone or a funnel, well, then we would have to worry about, as the water drains, that the radius gets smaller, right? Because the radius would change with time. But for this particular question, the radius doesn't change with time. So when you see his solution, understand that's not a leap in logic, but that's a shortcut that he's using in order to avoid a messier problem. So this all has to do with related rates, rate of change. Also, I want to say this. This first one here is simply related rates. That's section 2.6. This is how something is changing, how the rate of change is increasing or decreasing. So that's actually the rate of change of the rate of change, or in other words, kind of what we would think of as the second derivative or acceleration. And when you look at Part C actually comes from Chapter 6 when we do separation of variables. We did this mainly with slope fields, but this is where that type of problem kind of connects back to something else. So if you notice here, this is from Chapter 2. The middle question is kind of from Chapter 4, and this is from Chapter 6. So this is a type of AP question where they're asking you about a wide range of topics in a relatively short and simple question. This doesn't even have parts D, E, or F. It's just a three-part question, but it really is a wide spectrum. Please watch Mr. Smith's solution videos. There is a video for each of the three parts, and also look at the other video for the other question. Thank you.